Yes. Good afternoon, everyone. I'm Chetana Pujari, and on behalf of Manipal Institute of Technology, I welcome you all for the technical talk on fundamental of 3D graphics by Mr. Abhishek. So this talk is organized by Department of Information and Communication Technology. So our speaker, Mr. Abhishek, is a founder and MD at aiRender Technology Private Limited, a startup working on the next leap in video conferencing. aiRender is a part of the Venture Devil Startup Incubator Program at Arizona State University, US. Prior to this, he was engineering manager in computer architecture labs at Intel, leading a team of 20 engineers. He holds a MS degree in computer science from Arizona State University and was awarded Outstanding Graduation MS Student in Computer Science. He holds 3 US patent in 3D graphics architecture and has 4 ACM papers and IEEE journal publication to his credit. So now I request our speaker, Mr. Abhishek, to take over.
Good evening, everyone. Thanks a lot to respected HODs of the different departments at MIT, the faculty and students of MIT. Thanks for providing me an opportunity to present 3D graphics to the academic fraternity at Manipal Institute of Technology. And a special thanks to Professor Chetana for coordinating this talk and a great introduction for myself. With that, let me get to the topic for today, that's 3D graphics. Here's the company website link and the 2D video conferencing app that we have come up with and the YouTube channel for our company. Please do check these out. Here is the agenda for today. Let me get to the first section. So our universe exists in multiple dimensions, possibly more than 10. An average human being can perceive the world around him or her in 3-dimensional space. Most existing computer applications visualize the space in 2 dimensions. In the last century, with the introduction of computer-generated graphics, many applications have started visualizing the world in 3 dimensions. Today, we are going to take a walk through the world of 3D graphics. Have you ever wondered how 3D games like Counter-Strike, Pokemon, Fortnite, and City Racing work? How do popular 3D software like AutoCAD, Maya, or Unity bring 3D objects, models, and 3D world into action? Now, a 3D game or a 3D world scene can be considered like a movie which is arranged as a deck of frames or images and are played in sequence. Each frame is constructed by converting a world modeled in 3D to a 2D image, a process known as rendering. As an illustration, let's take a look at the rotating cube on the left side. Rendering basically converts the view of the cube from a particular angle and projects it in 2 dimensions onto the computer screen, as shown on the right side. We are going to get introduced to 3D coordinate geometry. Let's take a look at a simple 3D example at your home. Here is a typical dining table. You can see the shape of the dining table is made out of multiple rectangles. For one of the rectangles shown in the previous slide as part of the dining table, let's now define the coordinates. The rectangle has a length of, let's say, 2 units and the width of 1 unit. So the rectangle can be split into 2 triangles. One of the triangles has the following coordinates in Euclidean or XYZ coordinate space: 0, 0, 0, 0, 1, 0, and 2, 0, 0, as shown here. And similarly, all coordinates of the table can be defined. Okay. In this section, we will introduce you to different spaces and the concept of transformations in 3D graphics. Primarily, there are 5 major spaces and 4 main transformations in 3D graphics. First of all, there is local space, which deals with creation of local objects. Then comes world space, which positions multiple objects in a 3D scene. Then we have the view space, which sees the world from a viewer's or camera's point of view. Further on, there is clip space, which clips the portion of objects to be shown in the screen and adds perspective projection. Finally, there is screen space, which maps normalized clip space coordinates to a pixel on the screen, for example, a 800 cross 600 screen. Let's first touch upon the first two spaces that we saw in the prior slide and the transformations between them. Think of local space as the 3D coordinate space in which a single object is created. For example, the tabletop in the example we showed in the last section is a local object in the shape of a cuboid as shown here, and can be defined with its own 3D space with its XYZ axis and origin. Similarly, a table with the tabletop and its 4 legs and an almirah next to it can be considered to be part of the world space in a specific 3D scene, where they are defined within a common global 3D space with a common origin and XYZ axis. The model matrix, which transforms local objects from its individual local spaces to a common vertex space or a common world space consists of transformations like translation, scaling, and rotation of vertices of these local objects. Now let's see what a 3D transform consists of. A 3D transformation is essentially a matrix to vertex vector multiplication. The transformation matrix is a 4x4 matrix. The vector contains a 3D attribute of a vector of an object, for example, XYZ geometry coordinates. The vector is 4-dimensional or can be considered as a 4x1 matrix for all practical purposes. The 3D transformation performs a dot product matrix vector multiplication of the 4x4 transformation matrix shown here on the left with the 4x1 3D attribute vector which contains XYZ coordinates to obtain a 4x1 transform matrix. And the same transformation is generally applied to all vertices of an object. The model matrix mentioned in the last slide performs a translation, rotation, or scaling, or a combination of these for all vertices of an object in a local space to transform it to the global world space. Now, the objects in the world space can be viewed from different angles. For example, we can place the camera on front, top, bottom, or sides, or at specific angles. Here you can see the top view of the two objects after transformation to the view space. View space is also called as eye space or camera space. Now, viewing the exterior through a window from your room can best explain the transformation from view space to clip space. This is similar to placing the objects in view space into the rectangular window of the world visible through a computer monitor. Some objects like the boundary wall in the picture shown here gets clipped. Some of the plants which falls within the boundary of the viewing window is included within the clip space and are shown completely on the screen, while some of the other objects like the gate and the kennel on the left and right sides of the viewing window respectively get discarded. Now, screen space converts clip space objects to pixels on the screen. The screen may be of the resolution 1920 x 1080 pixels for this laptop or 480 x 900 pixels for a mobile phone for that matter. Now we are going to view orthographic and perspective projections and frustum in this section. To understand orthographic projection, let's consider Bombay-Pune Expressway and viewing it from a helicopter or a drone. For most part, one of its lanes appears like two parallel lines at both sides of the road for a straight stretch of the road. This is an orthographic view of the road. Typically, orthographic projections are done for faraway objects. The orthographic frustum view shows near plane and far plane parallel to each other, and most importantly, similar sized in terms of what can be viewed within it. Think of near plane as a computer monitor and far plane as the plane including the farthest object you can see within the scene, and parallel to the computer monitor screen or the near plane. The planes are near and far with respect to the viewer's eye or camera position. The space between the near plane and far plane is called a viewing box. The viewing box of orthographic projection is a cube-like frustum box. As you can see, the objects which fall completely within the viewing box, like the green cube over here, is completely visible and included in the view. The red cube which falls on outside the view box is discarded, and the blue cube which falls on the boundary of the viewing box is clipped. Now here is the perspective projection of the same lane from Bombay-Pune Expressway. If you stand on the lane and view the far stretch of the straight road, as far as you can view, the two edges of the road seem to merge towards the far stretch as shown here. The distance between the edges seem to be wider towards you and seem to be closer towards the far end of the road. This is a typical example of perspective projection and takes real life perspective view of the scene. If you have gone to a drawing competition for small kids, you can see most of the pictures, be it for roads or houses, are drawn as orthographic projections. Most of the engineering drawings are orthographic projections, whereas the great paintings of Da Vinci or Raja Ravivarma capture perspective projections. Farther objects in orthographic projections seem to be same size as nearer objects, and that creates sort of a weird view of the scene. Now let's stand in awe of the simplicity of the frustum view of the perspective projection. Again, the laptop screen can be considered as the near plane, and the place containing the farthest object in the scene can be taken as the far plane. The length and height of the far plane seems larger than the near plane. The four sides joining far plane and near plane are trapezoidal in shape, as you can see here. Here again, the objects within the view box or clip space volume, as it is called, like the blue cube, are captured in the view. The ones on the boundary, like the red cube, are clipped, and the green cube outside the frustum view is discarded. Now, there are three parameters that define a camera's viewing direction. Imagine a fighter plane. Consider the X, Y, and Z axis of the plane as shown in the figure. The rotation about the Y axis and the XC plane is called yaw, and the rotation about the X axis and the YC plane is known as pitch. And finally, the rotation about the Z axis and in the XY plane is known as roll. The rotations can be in clockwise or anti-clockwise directions. Similarly, a camera can be rotated along this axis and positioned for a particular view of the scene with specific yaw, pitch, and roll parameters. In this section, we are going to take a deep dive into depth. To understand depth, consider a chair that's behind a trolley bag or a paper on top of a chair. The portion of the chair that's behind the paper or the trolley bag will not be visible and hence doesn't need to be rendered. The structure we use to record the depth of different objects to check which object is in front of the other object is called depth buffer. The depth buffer has values ranging from 0 to 1 for all pixels on the computer screen. 0 represents the near plane, corresponding to the objects that are closest to the camera, and 1 corresponds to the far plane, which relates to the objects that are farthest in the scene from the eye view. So an object X, which is in front of an object Y, will have a smaller value of depth versus Y in the range 0 to 1.0. Before you receive any objects to render, all values in the depth buffer are initialized to 1, setting them as farthest in the scene. In a previous section on Introduction to Coordinate Geometry, objects are shown to be built from multiple triangles. Depth corresponds to z coordinates of vertices of triangles. Now let's consider a triangle from the upper left half of the chair, as shown here. Imagine a rectangle covering that triangle with its sides parallel to the length and breadth of the computer screen. For sake of simplicity, assume all vertices of that triangle have a depth value of 0.8 corresponding to their z coordinates. So this triangle passes the depth testing, and corresponding locations in the depth buffer, as shown here on the right, are marked as 0.8. These locations map to the imaginary rectangle covering the triangle. The depth test pass means this chair triangle will continue through further steps of rendering. Now comes a triangle from the trolley bag towards the bottom, as shown here, which doesn't overlap with any portion of the chair. So this triangle also passes depth testing similar to the previous one, and the respective locations in the depth buffer with its are marked with its depth value of 0.5. Now let's consider a triangle from the chair that overlaps with the trolley bag and towards the middle of the scene as shown. Since this triangle is the one to reach depth testing first, it passes depth test and mapping locations in the depth buffer are marked as 0.8. And here comes a triangle from the trolley bag which overlaps with the previous triangle from the chair towards the middle of the scene. Note that the depth of the trolley triangle is 0.5 and less than 0.8 depth of the chair triangle. So it passes the depth test and mapping locations in the depth buffer are overwritten with its depth value of 0.5. On the other hand, assume the same trolley triangle came for depth testing before the middle scene chair triangle. It passes depth test and the depth buffer locations are marked as 0.5 as shown here on the right. Since the chair triangle came for depth testing after the overlapping trolley triangle, it fails depth test as its depth is 0.8 and higher than the trolley triangle's 0.5. The chair triangle is therefore discarded for further rendering. In this section, we will play with stencils. Stencil is pretty much.
Is there any tool to automate it? Like on what basis you're selecting the specific area?
So the bounding box, there is a particular calculation with respect to it. So the rectangle that's covering the triangle over here, for example, can be calculated mathematically based on the vertex locations of the triangle. So for example, this is the leftmost vertex, this is the top vertex, and this is the bottom vertex, right? So based on the leftmost vertex, you can specify the left side of the rectangle. Based on that top vertex, you can identify the top side. Similarly, the right and bottom sides can be defined based on the rightmost vertex, essentially. So similarly, for different shape triangles, you can identify that rectangular bounding box for each triangle in a mathematical manner. So essentially, the whole thing can be automated. In a graphics processing unit, there will be a mathematical computing unit which will compute the bounding box for each triangle.
So in the tool like Unity, whether such options are available, sir?
Yes, in Unity and Unreal game engines, there are API functions to calculate these bounding boxes, which will translate, which will be translated by the drivers and the underlying, let's say, DirectX or the OpenGL stack to the corresponding GPU hardware functions.
Okay, thank you, sir.
Okay. Stencil is pretty much same as the stationary stencil that most of you had used in your schools. Typically, it's used for showing alphabets and numericals in a 3D graphic scene, and at the same time ensuring the background 3D graphic scenes are rendered without any disruptions. Here are a couple of real-life examples of 3D graphic scenes, games, in fact, that utilize Stencil. As you can see on the left bottom corner, the player one Lakshman is being shown using Stencil. Here the alphabets in Lakshman are sort of carved out using Stencil, and the background 3D graphic scene of the game is visible through the letters, while the box containing the alphabets of Lakshman occlude the background 3D scene. Similarly, Stencil is used to showcase the options of different guns of the game player and the score as shown on the top right corner. Stencil testing is implemented using Stencil buffer. It's similar to the depth buffer shown in the last section. Stencil values of 0 to 1 are used in the stencil buffer to indicate whether or not to render each pixel on the screen based on a stencil mask. All values in the stencil buffer are initialized to 1, indicating these are, there will be a stencil mask that would be coming in. Here is a stencil mask which shows the letter L in Lakshman. As you can see, the locations in the stencil buffer mapping to the portion of the 3D graphics game scene visible through the region of alphabet L are marked as 1, indicating its visibility. At the same time, the stencil buffer locations mapping to the brown box covering the stencil mask for letter L are all set to a value of 0, which indicates the mask will be occluding or covering the background region. That's pretty much the world of stencil testing. In this section, we will see the dark side of backface culling. The most popular face culling method is backface culling. Consider the tabletop that we had seen in the prior sections. If the viewer or the camera is seeing the top view of the tabletop, the top face of the tabletop is visible and the bottom face of the tabletop is not seen by the viewer. The top face and the bottom face of the tabletop are rectangular in shape and are made up of 2 triangles each, as shown in the previous sections. In order to perform backface culling, we assign a winding order to the vertices of each triangle. From the exterior of the tabletop, vertices of all triangles are numbered incrementally in a counterclockwise direction. The vertices are numbered in counterclockwise direction as if the triangle is facing you. As you can see, the vertices of one of the triangles on the top face of the tabletop are numbered from 1 to 3 in counterclockwise direction. Similarly, the vertices of one of the triangles on the bottom side of the tabletop are numbered from 4 to 6 in counterclockwise direction. If you assume that the triangle is facing you, in this case from the bottom side. But when you are viewing it from the top, the winding order of the vertices of the bottom face triangle becomes clockwise as shown here. Now all the triangles with clockwise winding order are culled and rest of the triangles with counterclockwise winding are retained and are visible. Hence, the bottom face of the tabletop is not visible and only the top face is visible to the viewer. Now this section is going to delve into one of the most important topics in 3D graphics rendering called rasterization. Most of you may be familiar with the raster scanning methods in older televisions. As we have seen in one of the earlier sections, 3D objects are made from 3D polygons and 3D polygons are made from triangles, which are the basic building blocks of 3D objects. As you can see here, the tabletop is a rectangle, which is a polygon, and it consists of 2 triangles. Now, rasterization in essence involves converting triangles of 3D objects in the 3D scene into pixels on the computer screen. The basic requirements for rasterizing two adjacent triangles, that is triangles that share a common edge, involves it should not leave any holes, that is non-rasterized pixels, between the two adjacent triangles so that the rasterized area is completely filled. No pixel is rasterized more than once, that is the rasterized triangles should not overlap. In order to achieve these requirements, certain rasterization rules are established. One set of such rules is top left rule. It states that a pixel is rasterized if and only if its center lies completely inside the triangle, or its center lies exactly on the triangle edge, that is either top or left edge. In case of corners, the pixel center lies exactly on the multiple edges, that is top or left edges. A top edge is an edge that is exactly horizontal and lies above other edges. And a left edge is a non-horizontal edge that is on the left side of the triangle. As you can see in the figure, the red edge in the triangle on the left is a left edge, and the red edge in the triangle on the right is a top edge. Now let's go through a rasterization algorithm. There are different algorithms for that matter for rasterization, but we'll go through one of them. In order to reduce the number of pixels that need to be traversed as part of rasterization for each triangle, the algorithm computes a bounding box for the triangle to be rasterized. Computing the bounding box essentially involves finding the minimum and maximum x and y coordinates of the three vertices making up the triangle in raster space, as shown here. Now, once you compute the bounding box of the triangle, the next step is to iterate only over the pixels within the bounding box to rasterize the triangle, rather than rasterizing over the entire set of pixels on the computer screen for each and every triangle. Now, rasterization checks whether each pixel in the bounding box is inside or outside the triangle using the same set of rasterization rules we discussed in the prior slide. Now, this section helps you learn how to sample texture maps. First of all, let's see why do we need texture sampling. Let's take an example of a high quality 3D face, like the one shown on the right side. A typical high quality 3D face requires anywhere between 40,000 to 60,000 vertices or more. If we were to color each vertex separately, it requires an RGB color value per vertex amounting to around 40,000 to 60,000 RGB color values. That takes a lot of space in the RAM memory to store these values. Now, instead, let's consider a texture map. Think of a texture map as a blanket wrapped over the 3D object. For example, consider the tabletop shown below. We can wrap it with a texture map of plywood texture as shown here. Typically, texture maps are stored as single image or multiple images. Here, the plywood texture image is shown on the right and has a width of 400 pixels and a height of 200 pixels. The texture coordinates in the axis along the width or the x-axis are called u coordinates, and the ones along the height or the y-axis are called v coordinates. UV coordinates, as you can see here, are scaled from 0 to 1. Now consider the top facing part of the 3D tabletop object that we had seen in the prior slides. The rectangular tabletop can be split into two triangles, and the XYZ coordinates of the vertices of the triangle are as shown below. Now the vertices of the top right triangle are mapped to UV coordinates in the plywood texture image. For example, the top right corner vertex with XYZ coordinates 210 are mapped to a pixel location with UV coordinates 0.8 and 0.9 in the texture image, and the corresponding RGB value of that pixel is mapped as the color value for that vertex over here. Similarly, other vertices of the triangle can be mapped to different UV coordinates in the texture image as shown here. The advantage with storing such a texture map is that it can be reutilized for texture mapping the same person's face or this tabletop object in different scenes in a 3D graphics application. This section will introduce you to the concept of shaders in 3D graphics. Before going into shaders, let's see how a typical 3D graphics pipeline looks like. A 3D graphics application is fed by the grain programmer or the graphics application programmer to the 3D graphics pipeline, which is implemented in both software and hardware. Different blocks in the 3D pipeline are shown here, and we have already gone through most of these blocks in detail in prior sections, like clipping, culling, rasterization, depth, stencil testing, texture mapping, etc. For now, we'll focus on vertex and fragment shader blocks. Each block in the pipeline has a specific function, as explained in the previous sections. Now, some of these blocks are programmable and can be customized by the game programmer, like the vertex shader and the fragment shader. Mostly the vertex locations and pixel colors of each vertex and each pixel are independent of other vertices and other pixels, or only dependent on the neighboring vertices or pixels. So the vertex and fragment shaders are highly parallel small programming blocks. Now let's see what's a vertex shader. It primarily performs transformation of X, Y, Z location coordinates or other attributes like normals of vertices or triangles in a 3D object. It performs rotation, translation, or scaling or zooming or other similar transformations of the triangles that we discussed in one of the previous sections. The diagram here shows the rotation of the vertices of a triangle. Vertex shaders takes the 3D XYZ coordinates or other attributes of a single vertex as its input. Similarly, the output of the vertex shader consists of the transformed 3D coordinates or vertex attributes of a single vertex. And multiple vertex transformations are compiled using vertex shaders in a parallel manner. Now, the primary function of a fragment shader or pixel shader is to determine the final color of a pixel. The input to the pixel shader is the initial color of a single pixel. For example, it can be the color of the nearest vertex to the pixel, or it can be fed with a uniform color for the triangle. The input pixel is obtained after rasterization of triangles to pixels and possibly after depth and stencil testing, as shown in the diagram on the right. The output of the pixel shader is the final color of the pixel as shown in the diagram of the rasterized pixels of a triangle on the bottom right. The pixel shader may run lighting algorithms or shadow algorithms, which we can see in detail in future sessions. Now, lighting in 3D graphics is a comprehensive topic in itself. If you like this session, we can plan for a session on lighting related topics in the future. Now, here is the YouTube link for the 3D graphics topics covered in today's talk. Please check it out. Now, regarding our startup, aiRender is building an AI-based real-time live streaming in thin air 3D video conferencing software solution, Hi 3D Meeting for greater reality. We have a web-based Hi 3D Meeting video conferencing app ready, as you can see on the left, showing my 2D video and the corresponding reconstructed 3D video during the call. The underlying AI engine based on neural networks, AirBrain, is also ready, as shown here on the top, converting my teammates' 2D video to 3D. As shown in the video below, we have launched Hi 2D video conferencing app, which is a precursor to the 3D meeting launch. We have internship openings for 4 profiles. First profile is on machine learning or neural networks for a data science based internship, and it's based on 2D to 3D reconstruction of human faces. The second one is on 3D graphics rendering using game engines like Unreal Engine and WebGL framework to enable 3D rendering of 2D to 3D reconstructed videos of human faces. The next one is full stack mobile and app development for video conferencing apps. And the fourth profile is in business development, where you get a first-hand experience in marketing, sales, finance, operations, market analysis, and competitive analysis. The internship candidate for the 2D to 3D face reconstruction in the data science profile will be working on machine learning algorithms to improve the quality of human face using CNN and GAN and similar neural networks and associated loss functions, and add reconstruction capabilities for the back side of the human face, the front side of the human face, the teeth, the ears, hair, and human body, and to improve the speed of inference and training. The 3D graphics rendering intern candidate will be working on developing a 3D engine to render the human face real time using Unreal Game Engine and WebGL based JavaScript APIs from 2D to 3D reconstructed videos of human faces obtained from our high video conferencing app and AirBrain 2D to 3D machine learning engine. The mobile app and web development internship candidate will be working on full stack development of video conferencing web app and Android and iOS mobile apps using React, JavaScript, HTML, CSS, etc., and an open source audio video communication framework called WebRTC based on C and JavaScript. The business development intern will be getting a first-hand experience in marketing, sales, competitive analysis, market analysis, in preparing investor pitches and customer pitches, in projecting company-related financial requirements for investor pitches, and in driving social media campaigns and outreach. Thank you all. Now we can open the floor for questions from the audience.
If you have any queries with respect to the session, or you have any queries with respect to an internship, you can please feel free to ask the question, or you can post it in the chat section as well.
So how do you apply for the internship?
So I have shared the internship profile and the email IDs to contact to the respective department HODs, and they'll be sharing the profiles with the respective departments. I mean the students in respective departments. You can send me your resumes through those email IDs.
Sir, could you please show that slide in which 2D to 3D transformation is visible? A meeting, some 2D to 3D meeting.
Yes. This one?
Yeah, this one. How can we distinguish by looking at the image? Which one is 3D or 2D? Like.
Yeah, from an image, I mean, it's not a clear indication, but so essentially we will be introducing these products initially in an AR VR headset based or a 3D TV based environment where you can distinguish clearly between the 3D reconstructed face versus the 2D video images. Here, for example, I mean, so this is a, I mean, what do you say, a snapshot of the video. I have the actual video in case you guys are interested. I can share with you where it shows when you move your mouse, right? You can in fact turn the, I mean, see the sides of the face and all as it is a 3D representation.
And one more question, please.
Yeah.
What about the components in a 2D pipeline and 3D pipeline? I think only few components are additional in 3D pipeline.
Not exactly. So for example, if you consider the, I mean, graphics processing unit hardware for 3D pipeline and 2D pipeline, the 2D pipeline is typically called media pipeline. Okay. So the components that I mentioned in the pipeline over here, these are typically the components that you see in a 3D graphics pipeline. There will be like vertex shading unit, there will be clipping unit, culling unit, there will be a rasterization unit, separate depth and stencil units. Then there will be pixel shading units. Basically, the vertex shaders and pixel shaders will send their corresponding vertex shading and pixel shading algorithms to a set of massively parallel set of graphics processing execution unit cores, which are small FPU and extended math processing units. And then further on, the texture mapping and all are done, and the eventual rendered image from the 3D scene is returned to the frame buffer. So this is a typical 3D graphics pipeline, whereas in the case of 2D pipeline, so you might have heard about this MPEG algorithms or the codecs like H.264, AV1, etc. So essentially, in a video, if you see, let's say the video is showing my face moving from left to right, right? It's most of the part is similar, as in it is showing my face, right? But then there is gradual movement between frames when I'm moving my face from left to right, right? So what it does is, so for the starting scene, it has to show the entire face, right? Now for the next frame, so for example, like in a second, typically you show anywhere between 30 to 60 frames per second, so that the eye cannot notice the lag or anything between the frames, right? Now the next frame is a small movement from left to right. So you basically capture the the differences between the second frame and the first frame, which is a minor difference in terms of faces. Probably the background is not even changing, right? So you can segment the entire image into multiple blocks where in certain sections the image or let's say, for example, my face is changing, right, slightly, whereas the background part is not changing, right? So only the blocks that are changed will be processed, and there are certain video codec related algorithms, and there will be hardware blocks running those, which will be doing the 2D rendering for that. For example, like, so the change in the particular pixel location, let's say on my nose from the first frame to second frame, is known as a motion vector. So such differences in the motion of that particular pixel is calculated using certain hardware components corresponding to that, and only those portions are rendered onto the scene. The rest of the background image pretty much remains the same.
Okay, thank you, sir. Thank you.
Sir, actually, in today's talk, students from different departments have joined. They have selected computer graphics as their open elective course. That's why you can see students from automobile, mechatronics, and other departments. So I think even they would be interested to join the internship. So if you could say something like.
Sure. Yeah, please feel free to share the internship profiles with the respective department contacts, and they can also apply for the internship. We'll go through their resumes and see if their background matches our internship requirements, and we'll give them a call accordingly.
Okay. Okay, sir. So I think.
Do you use any deep learning algorithms, sir, for this?
Yes. So in fact, like you see here, right, the 2D video and the corresponding 3D video. This is reconstructed using, so you see there is a skin part of the face, which includes the forehead, nose, lips, eyes, eyelashes, etc., and the contour of the face. And then there is like the hair and the ears. So we have separate machine learning algorithms to convert 2D to 3D. It basically uses some advanced variants of convolutional neural networks and generative adversarial networks in order to reconstruct 2D to 3D. So it basically, if you see, it reconstruct the geometry, the lighting components, and basically the color of the respective triangles within the vertices and triangles within the 3D geometry. It's using convolutional neural network.
We have something called as
GANs. Sorry.
Yeah, we have something called as slow fast network and something like that. Does that have any relevance here?
No, we haven't used slow fast networks here. Currently, we are primarily using CNNs and GANs. In future, we plan to use certain other techniques also. For example, some of the techniques related to super resolution in order to improve the quality of the resolution of the 3D face that you are going to reconstruct.
So this must be taking you very long for training days together.
Not really. It depends upon so the kind of GPU instance. For example, we are training this on GPU instances on cloud, which are reasonably powerful GPUs, and we are feeding basically multiple frames from the 2D input as batches, and those are done in parallel. So when we started, for example, so essentially you have to achieve this 2D to 3D reconstruction, ensuring, let's say, 30 FPS rendering, 3D rendering. And since it's a video conferencing application, there is a latency between, transporting these audio-video components from video frames from each participant to the cloud, and the reconstructed 3D frames to each participant, right? So considering that, let's assume like 30 FPS is the frames per second rendering that you want to show, and let's assume a typical 35 millisecond latency in terms of video transfer between the participants through the communication framework. So essentially, within a matter of like anywhere between 20 to 60 milliseconds, you have to do this 2D to 3D rendering. So when we started, each frame was kind of taking close to 17 seconds. Okay, it was pretty slow. And then we applied certain techniques in order to speed up different components involved in the, it's after training, we do the testing part of it, right? So we applied certain techniques in order to speed up the inference part of it. And eventually, currently, we are able to achieve somewhere close to like 170 millisecond 2D to 3D rendering latency. And we are further trying to bring it down somewhere close to like 30 milliseconds or so. So currently we are achieved close to like 100x in terms of performance improvement. We are trying to bring that further down so that there are no delays when you finally render the 3D onto the screen.
That's nice.
So is it that all the frames are being done in the video, or is it like key frames are being identified and only those key frames it is converted into 3D?
Not only keyframes. Currently, if it's rendered at, the 2D video, if it's rendered at 30 frames per second, we are currently using all 30 frames. But eventually, our plan is to reduce, identify the keyframes, right? In 2D video, typically there is this I, P, and B frames where the the I frames constitute the keyframes. So you identify the keyframes and do complete 2D to 3D rendering for them. And for rest of the P and B frames, you only do the 3D reconstruction for the motion vectors.
Okay, thank you.
Sir, one doubt, like each frame the model is reconstructed, or is the model constructed once and animations are applied?
For each frame, the model, the model is not reconstructed. Basically, the 3D graphics object, right? That is reconstructed essentially. So it passes through the model's inferencing portion, and for each frame it is reconstructed currently. But like I said, we are trying to reduce the computational complexity by only doing it for keyframes, and for rest of the frames, you do the 2D to 3D reconstruction for only the motion vectors.
So if no queries, we can conclude it here.
Thanks a lot, Professor Chetana and Professor Smitha, for coordinating this talk. Thanks a lot to all students who have attended.
Yeah, on behalf of our department and Manipal Institute of Technology, even we are very thankful to you that you spent 1 hour of your time and gave this insightful session to us. Thank you, sir.
Sure. The pleasure was all mine. Thank you.
Yeah, thank you so much for the session. I think it was very informative and many queries came up, and definitely I think many more will join the internship. Yeah, thanks a lot from ICT department to Abhishek. Look, the students, there will be one more session on I can't exactly remember the title. Sir, you remember the title?
Oh, yeah, there is one on customer development, I mean, customer discovery and the road to
Hello.
problem market fit, essentially.
Okay, so sir is going to give this particular session sometime at the end of this month, I think. So you request the
Hello.
students to join the session and take advantage of it. Yeah, thank you all for joining this session. Have a nice day.